Hi, everyone. Thank you for joining us. My name is Dion Rossiter, and I am here from Science at Cal along with Berkeley Labs. And we are here today for a changing landscape, wildfire dynamics in California. And we are joined with Faji Mena and Katya Rakhmatulina. And I will go ahead and begin by giving you a brief introduction of Science at Cal, one of our partners for today's program. So we are a program at UC Berkeley in the Lawrence Hall of Science, where we really create opportunities for the scientists across campus to celebrate science with the public through all kinds of different programs like science cafes, lectures, festivals, and more. Historically, all of our programs have been in-person programs. So obviously we had to, switch tasks and pivot, as we're all calling it, and start creating these online opportunities for you, our community, the public across the East Bay, and hopefully we have people from afar joining us that are new to our programming. You can join our listserv and learn all about science that's happening at Science at Cal. You can learn about all of our programming, including programs like this and more. I know we have the Bay Area Science Festival coming up, so we'll be hosting a slew of programs for the public through that program as well. You can email us to learn more. You can follow us on both on Facebook, Twitter, and Instagram, as you see here. So I'm going to just hand things over to Jen, my partner at Berkeley Lab, and once she takes over and describes, how this partnership came about, we'll go through and begin our program. You'll be able to answer questions throughout the entire show, so please use that chat function as much as you can. We really want to create a dialogue with our speakers. We'll have opportunities after each one of their talks, and we'll have opportunities at the very end to have a very lively discussion with both of them and the audience. So feel free to constantly be asking those questions. We'll answer anything you like to know about fire and water storage in California. And the last thing is that this program will be recorded. So if you want to share this program with your friends or want to watch it again later, we will give you that opportunity. So go ahead, Jen, why don't you take it away?
Wonderful. Thanks so much, Dee. Hi, folks. My name is Jen Tang, and I'm the Manager for Federal and Community Relations at Lawrence Berkeley National Laboratory. For those who don't know, Berkeley Lab is one of 17 U.S. Department of Energy national laboratories across the country that are tackling the critical scientific challenges of our time. The lab is supported by DOE through its Office of Science and is managed by the University of California. Since its founding nearly 90 years ago by a UC Berkeley physics professor named Ernest Lawrence, Berkeley Lab has been dedicated to advancing the scope of human knowledge and seeking science solutions to some of the greatest problems facing humankind. Today, Berkeley Lab researchers develop sustainable energy and environmental solutions, create useful new materials, advance the frontiers of computing, and probe the mysteries of life, matter, and the universe. All of the research at Berkeley Lab is unclassified. Our main campus is nestled in the Berkeley Hills northeast of the UC Berkeley campus, and we employ approximately 4,000 people, about 1,700 of whom are scientists, engineers, and faculty members. And more than 500 of our employees are undergraduate and graduate students, scientists just beginning their research journey. Berkeley Lab's proximity to Cal and our close ties to the UC system create a really unique and synergistic environment for scientific discovery. Many of our members of our community are affiliated with one of the UC campuses as students, postdocs, and professors with joint appointments at the lab. As you can imagine, Berkeley Lab's relationship with UC Berkeley is especially close, and our institutions have joined forces to advance science across many frontiers. One of the main motivations for this Midday Science Cafe series is to share with you examples of compelling and complementary scientific research from both of our institutions. We hope you enjoy today's presentation on the changing landscape in California, and we look forward to highlighting other science stories in the months ahead. So in addition to typing in questions for our presenters today in the chat function, we'd love to hear from you if there are any topics you'd like to hear about from us in the future. And with that, I will turn it back over to you, Dee. Thanks so much.
Great, thank you. And I will go ahead and give a quick introduction of our first speaker, Katya Rakhmatulina. And Katya is a PhD candidate in environmental engineering at the University of California, Berkeley. She's interested in complex interactions between wildfires, hydrology, ecology, and climate change. The results of her research will aid watershed management decisions with the goal of minimizing catastrophic fires, promoting landscape diversity, and increasing water yield. Katya uses a medium for science engagement and uses art as a medium for science engagement and is an illustrator for Berkeley Science Review. So a scientist and an artist. It's great to have you, Katya.
Thank you. Let me share screen. Hello, thank you for coming to this talk, and I will talk about wildfire management in California, specifically its impacts on our watersheds, and some lessons that we learned today and some things that we learned about tomorrow with some modeling. Okay, so I want to start off this conversation by saying that between 60 and 90% of California's water supply does originate in the Sierra Nevada, which is a fire-prone ecosystem. So whatever disturbance happens in the Sierra Nevadas might have some downstream effects on urban centers. And the disturbance in our case is wildfire. And so what does that look like? It looks like the snowy Sierra Nevadas that store a lot of water, and then in the springtime the snow melts and it's being delivered through different streams and rivers to urban centers such as the Bay Area, and then there's a lot of dams that control the flow. So it's a pretty extensive network. And because California is a land of extremes, I want to show you this picture where on the left you see Sierra Nevadas covered with a lot of snow, so a huge snowpack, which will result in a lot of spring snow melt, which actually could be damaging to infrastructure if we cannot hold it all in one place. However, only a year later, there's the picture on the right where there's not a lot of snow. So that means we could have drought and in general might have just drier conditions, which would promote wildfires. And then, because California is a land of extremes, I will continue talking about the fact that we also have a forest issue. So we have a pretty long history of forest management in the United States, especially in the Western United States. And here's a picture on the left of Yosemite National Park before fire suppression policies were put in effect. And essentially, fire suppression policies in the US mean that any fire that started had to be extinguished. Thanks Smokey the Bear, saying that only you can prevent wildfires. Again, it's a pretty extreme policy that if a fire starts, it's extinguished. And what does it cause? Well, on the picture on the right is Yosemite, about 100 years after wildfire suppression policies came into effect. And what you see is that it's a lot denser forest. The trees are really close to each other. So if a fire starts in the middle here, it will spread to other fires and become quite large. So for the longest time, we used fire suppression policies, but then soon scientists realized that wildfire perhaps is a tool in the ecosystem that is a natural part of it. And the first studies were the giant sequoia studies, where people noticed that the groves were not getting any larger and there are no new trees growing. And that is because giant sequoia rely on fire. The cones are serotinous, which means that they just need heat to start growing. Okay, so got studies. However, I'm gonna again jump to extremes. In 2018, we have Camp Fire, which is one of the largest fires in California, and is a result of some fire suppression policies, just because we have a climate change with warming temperatures and the fuels getting drier. So once a fire does start, just because there's so much density of material that can burn, it becomes catastrophic and we cannot extinguish it. And of course, that causes air pollution. It displaced a lot of people. Some people died and a lot of structures were damaged. So politically, people definitely realize that we have a forest management issue right now, but what do we do about it? There's not much that we know right now, other than we need to fix it. Okay, again, California has a wildfire problem. What is being done about it? Well, first I'm gonna mention that some things are being done about it. The policies are shifting, and some of the first places in the United States that did reintroduce wildfires back into the environment are the national parks. And this is Yosemite National Park, and the sign reads, "Management, fire, do not report." So this new idea of wildfire management has emerged, and from now on, whenever I talk about wildfire management, I mean allowing wildfires to burn if there's no threat to air quality, human lives, and structures. So if fire starts, it's not a threat, it's allowed to burn. Okay, I'm gonna focus my conversation even further on the Willet Creek Basin, which is the first basin to have a pretty long historical record of wildfire management. And what you see here is actually Willet Creek, and I do get to work here quite a lot, so I get to look at the beautiful views of Yosemite National Park. This basin is unique, and it has experienced over, since 1972, when wildfires were allowed to burn in it, 75% of the vegetated area did burn at least once. So that's quite a large area that did experience wildfires. So again, it's a natural laboratory where we could look at what kind of impacts wildfires have on stream flow. And as I mentioned earlier, we care about stream flow because the state of California really depends on the Sierra Nevada hydrology. Okay, so what did those fires do to Willet Creek Basin? The one really drastic thing is the vegetation shift in Willet Creek Basin. So the picture on the left is Willet in 1969, so that's before fires were allowed to burn. The biggest thing to note is that we have a really thick, dense area of forest. So again, if a fire starts burning here, you can imagine all those trees and fuels, fire will spread and might become quite large. And then after more than 40 years of wildfires burning through the landscape, we really see a shift in the landscape composition. We get a lot more meadows, we get shrubs, and so in general, the landscape is patchier, which is also good for ecological biodiversity and also not having huge fires, just because, and you get a mosaic of fires occurring. And this is what I'm going to show you in the video, where fires actually in the Willet look a lot like a jigsaw puzzle. Those are all fire perimeters, and the warmer colors just mean closer in time. So this is time series of fires occurring. And again, as one fire burns, the next one doesn't really overlap. And this behavior is called fuel limited fire behavior. There's not enough things to burn for the fires to really become out of control. And the previous fire perimeters influence the future fire perimeters. Okay, so again, hopefully I convince you that a lot of things have changed. And I was pretty lucky to actually witness the Empire Fire in August 2017 during my PhD. And in fact, we actually have weather stations around the area that the fire burned through, which was really interesting for me to observe. And for those of you who don't know what wildfires do to the landscape, I will show you some pictures. So here is the shrubland weather station that we have installed. And then before the fire, there were trees that were dead trees from a previous fire before that. So at some point, this vegetation was a forest, and now there's a lot of shrublands. And then the Empire Fire comes in and burns at high severity. So there's no more dead standing trees. The ground is bare. However, less than a season later, we get regrowth of shrubs. You can even see some wildflowers, which means the soil moisture could be higher. So again, the fire is doing quite a lot in the landscape. Okay, so this is the historical context for what is happening in this basin. And so far, it looks like wildfire management strategy has many benefits in the Willet. Smaller fires, biodiversity, patchy landscape, and we do see increases in soil moisture, which helps resilience of the ecosystem. Okay, again, but I'm talking about this presentation does focus on future climate, and for someone who maybe sees those benefits in the Willet today, wants to, like a forest manager, for example, wants to start wildfire management strategy in their basin, but in the future climate. So the question here is, what would happen in future climate? Will we still see the same benefits we've seen historically in this natural laboratory? Will we see them in future climate? Okay. So first we need to obtain future climate if you're going to talk about future climate. And here is the predicted temperature for Illinois Creek Basin, so a specific location. And we have two scenarios, the hot scenario and hotter scenario. Hotter scenario is actually business as usual scenario. So if we keep emitting the same CO2 that we do today, we will have a pretty drastic increase in the temperatures in this location in the Sierra Nevada. Hotter, not so much, but we still increase, or the hot scenario, even though we curb CO2 emissions, we still increase our temperatures. Okay, so temperatures increase, that's the summary. However, precipitation does not change. This is what I want to show with this graph, mostly that we roughly get the same totals of precipitation in the future climate. However, what we do observe, and I'm not showing it here, is that we do get more frequent drought and extreme precipitation events. So we do see extreme events, however, the totals are pretty similar. Okay, so have our climate record now. Now I'm going to briefly mention what a fire regime looks like. So fire regime has different characteristics. How big are the burn areas of, like, how big is any given fire? How severe is it? Like, what % of the area burns at high severity? And how often fires return to any specific location, such as a watershed? And what kind of vegetation grows after a wildfire? That's all important to the water, vegetation, hydrology interactions. Okay, so for our purposes, we're only going to increase in, fire frequency for a future scenario, and then look at how more frequent fires affect the watershed. And frequent fires might occur just because the temperatures are drier, so all the things can ignite more frequently, like such as fuels. Okay, again, have our fire scenarios, we have our climate scenarios. Now we put those through a model, and the model that we're using is really unique, and it combines the vegetation growth to climate to hydrology. So all the things are interconnected, and then you can introduce disturbance, so wildfires, and then what you get is stream flow time series and other variables. So I also can know about snowpack and soil moisture. However, what we care about is stream flow, just because that's something that's motivational to downstream communities for this presentation. So that's what I'm going to focus on. And so I'm going to jump straight to the results here. And this is a map of constant fire regime. So I picked a fire regime that's a historical one. So the bars that you see here is just occurrence of a wildfire that we have seen observed historically. So this is historical fire frequency. And then all the different lines you see are different climate scenarios. And this graph, anything above 0 essentially means we get an increase in stream flow. Because this is a model, we can control for the variable, and so the increase in stream flow is just from the introduction of wildfires to the model. Again, everything else is constant. And the biggest thing to notice here that the climate by itself does not really change the outcomes. We see the outcome where we do increase stream flow by roughly 23 millimeters per year. So again, that's kind of good news. Like, if we have a pretty similar fire regime to the one we observed historically, the climate change is not going to change our outcomes. Okay, well, what if you keep the climate constant? So here's the hot scenario, and I'm talking about period of 2030, 2070, by the way, just because that's when you could start implementing policies in roughly 10 years. But again, if the climate is constant, but we increase fire frequency, we actually reach the same hydrological outcomes. So we do see an increase in stream flow of roughly the same amount, but we see it quicker. Perhaps this is not that surprising because, again, as I mentioned, the wildfires are similar in size and burn severities. If we get a different type of fire, so if it's like a catastrophic fire with large areas, the outcomes could be different. Okay. And why do we all care about this? I want to put this in context and bring it back to the fact that I said that a lot of the urban areas rely on the water from the Sierra Nevada. So we have this aqueduct system from Hetch Hetchy Reservoir in Yosemite, and San Francisco gets 100% of its water from the Hetch Hetchy Reservoir. And so an increase between 19 and 29 millimeters of stream flow that we predicted for the future equates to roughly 5.7 to 8.7% of San Francisco's residential water use each year. So that's a pretty good number from a watershed that's, while it's not that small, it's not that large. It's 150 square kilometers. So there could be a much greater area that could be contributing to this increase in stream flow. Okay, and in terms of money, that means that's another motivational thing for policy and downstream users. The increase in stream flow equates to roughly between $6 and $9 million in water sales, and between $1.5 and $2.3 million in hydropower generation. So just to put some money on trying to manage our forests, there's some economical benefits. Okay, so in summary, California is water scarce and has an increasing number of catastrophic wildfires. So we have both forest and water issues. And despite the warming climate, managed wildfires in the Willamette did promote a healthy watershed. So we have this basin that we could study historically and what wildfires did do to it, despite the rising climate, even in historical timescales. But even with our future climate predictions for the period of 2030-2070, we still anticipate the same increase in stream flow from wildfires. And so essentially the conclusion here is that we, as forest managers and watershed managers, it is encouraging results to reintroduce wildfires on scales that could produce stream flow change. And that is all. Let me know if you have any questions. Thank you.
Thanks so much, Katya. That was a great presentation. We do have a couple questions we wanted to ask you before we turn things over to Faji. So our first question is, are there any best practices or lessons learned from the wildfire management strategy implemented in the Illilouette Creek Basin that could be applied to other wildfire-prone areas of the state? Or would you have to have individual wildfire management strategies to develop those for specific geographical regions?
Yeah, so I mean, certainly a lot of caution has to be used when applying what we learn in Illilouette Creek Basin specifically to other areas. So one advice is absolutely you cannot, like just from watching, like looking at me present results that are quite positive, not all basins would look like Illilouette Creek Basin. So to apply wildfire management strategy, you do have to make sure that the vegetation is roughly appropriate, the climate is roughly appropriate. So the lessons learned in Illilouette is that since 1972, there's not a single fire that became huge and out of control or like damaged anything. So that's good news. However, if the vegetation was, for example, a shrubland, this would be a different story. Yeah, so I guess my answer to that is you have, like, if someone's interested in implementing wildfire management strategy in a different watershed, they do have to be cautious, at least in the beginning. So pick, like, if a fire is starting in bad conditions, like do not allow it to occur, and then like learn from the first few fires what's going to happen. Yeah, and then pick areas that are very similar to the Creek Basin for start.
Thanks, Katya. Let me ask you one more question from our audience. Is fire suppression the norm outside of national parks in California? This question comes from somebody who wants to know if things have changed to stop catastrophic wildfires.
Yeah, fire suppression is still happening a lot, but that's because there's not a lot of areas that do not have structures close by. So a lot of the areas are wildland-urban interfaces, even though they could benefit from fire, it's just too much risk. And so what's really happening a lot of the times is that controlled burning and like manual removal of trees or like forest thinning is more common to try to prevent large-scale events from happening. But a lot of national forest land is taking the strategy on, and in fact, one of my other projects is in Sugarloaf Creek Basin, which is in Sequoia and Kings Canyon National Park. So most certainly, like the parks are using more and more wildfire use strategies, like just from like if a fire occurs, like let it be. But this basin is by far the longest the strategy has been implemented anywhere. Yeah.
Thanks so much, Katya. Appreciate you fielding a few questions. It's now my pleasure to introduce our next speaker, Dr. Faji Maina. Faji is a postdoc fellow in the Earth and Environmental Sciences area at Berkeley Lab, where she uses high-performance computing and remote sensing methods to understand the impacts of climate extremes and wildfires on water resources. She aims to provide a scientific basis that enables better understanding of how water resources will respond to extreme events such as wildfire and drought which may be increasing with climate change. Before joining Berkeley Lab, Vodji developed mathematical models to address water resource issues in France and Italy. She received her PhD in hydrology in 2016 from the University of Strasbourg in France, and was recently included in Forbes magazine's 30 Under 30 list for 2020. With that, I am going to turn it over to you, Vodji.
Thank you so much, Jennifer. So today I'm going to talk about how wildfire changes our landscape and how this landscape is going to change the hydrology in California. So as you may know, California has been experiencing severe and prolonged period of drought. As we can remember that back in 2014, all the reservoirs were dry because the weather was so warm. California is also experiencing unprecedented and frequent wildfire. We all remember Camp Fire in 2019. And this is just a glimpse of the future of California. The future is going to be warm, dry, and with frequent wildfire and devastating wildfires. And we need water in California. The state is home to 40 million people. Hence, we really need to understand how this new normal, how this severe drought and wildfire impact our hydrology. Wildfires have increased over the past decade by over 400% in California, and the burn area are just getting greater and greater over the year. In November 2019, as I mentioned before, with Camp Fire, Wildfire, and many other fires across the state of California, these wildfires are the costliest natural disaster in the United States, with the destruction of more than 100,000 hectares and displacement of many people in the state of California. The state of California is the most agricultural region in the United States and among the highest in the world. And the economy is also the highest in the world. If you look at the map of California, we see the Sierra Nevada mountain. Just Katya talked about it, and you're hosting Yosemite National Park and many other national parks. And we do have the Central Valley, which hosts the agricultural region. In the state of California, most of the precipitation fall in the form of snow in the Sierra Nevada, just Katya mentioned it. And this snow is going later to melt and to contribute to recharging the Central Valley aquifers. Unfortunately, the majority of wildfire in the state of California are occurring in the Sierra Nevada mountain, hosting these snow. So we really need to understand how these changes in hydrology and these changes of the perturbation due to wildfire impact our downstream water.
Hey, Vodji,
yeah?
can I interrupt you for just a second? I think as your mic hits against your sweater, it's causing some noises for the audience. Is it possible to hold it out, or?
Is it okay now?
Yeah. Yes, I think that'll be better if, yeah, it's coming from your computer. Okay, thank you so much, Vodji. Sorry to interrupt.
Is it okay now, I think?
Yep, I think it'll be fine. We'll test it out in the next, yep. Thank you.
Okay. Sorry for that. So to study how wildfire perturbation impact the water cycle in California, we study the Cosumnes watershed. And why do we select this watershed? Because most of the rivers in California have dams. And this watershed is one of the unique unique river in California without a major dam. And it's a large scale. So we really understand what's the water cycle in California. The Cosumnes watershed is also a representative Californian watershed. As I mentioned before, to be able to understand the water cycle in California, we really need to capture the Sierra Nevada and then the Central Valley. And we have this kind of dynamic in the Cosumnes watershed. We have the Sierra Nevada with forests, as we can see in this map down in green, with hosting forest, evergreen forest. And then we do have the Central Valley, which is the agricultural region with grape, alfalfa, and also the city of Sacramento. So in this watershed, we really capture the hydrodynamic in California, and we can really be able to understand the heart of circle in the state of California. To understand how wildfire changes our landscape and how this impacts hydrology, it's really important to develop mathematical models. First, pre- and post-fire measurement, like some scientists can go and do some measurement on site, but these measurements are often on small scale. And this small scale are insufficient to capture the water cycle of the total water cycle. As you can see in this picture, we do have this plot, we do have experiments on plot, and this plot does not capture like all the hydrology. To be able to simulate how wildfire changes our water cycle and how these impact our hydrology and our water storage, we need high resolution, high fidelity, and physics-based model, which simulates the water movement from the subsurface all the way to the atmosphere. And we need physics-based model because wildfires are complex and the hydrology of California is also complex. Unfortunately, these models are computationally expensive. So today we rely on high performance computing to be able to do this model. We use mathematical model to simulate the water cycle. In this model, we simulate everything from precipitation to transpiration, evaporation, storage, runoff, infiltration, how this water is going to infiltrate, how this water is going to discharge the groundwater and the groundwater flow. And we simulate all these processes in high resolution. In hydrology, high resolution means every hour, and in space, it's meter. And to do it, as I mentioned before, we use supercomputers and high-performance computers. So just to give you an idea, we need approximately 100 laptops running over 2 days to be able to simulate the water cycle in the Cosumnes watershed for just one water year. To understand how wildfire changes our water cycle in the Cosumnes watershed, we simulate for 5 years of water cycle, which covers the period from 2013 to 2017. And this includes the most severe drought over the past 1,200 years in California, followed by the wettest year on California record. And we assume that the wildfire occurred right after this severe drought in the state of California. And we are going to understand how this wildfire changes the hydrology. Before to do any kind of analysis with our model, we make sure that our model, the model that we develop to simulate the water cycle in the Cosumnes, is able to reproduce what's happening in reality. We make sure that our model captures all the dynamics like the snow measured by the satellite product, evapotranspiration, soil moisture, and many other variables. We make sure also that our model is able to reproduce ground measurements such as river stages and also groundwater level, as you can see in the two graphs that I'm showing down, that our model is able to reproduce the hydrology of the Cosumnes watershed. To simulate the wildfire, we rely on historic wildfire burn area. And this area are shown in purple in this map, and they represent around 20% of the total watershed area of the Cosumnes. To see how wildfire changes our landscape, before wildfire, as you can see on the left, we have a forest, a green forest, a dense forest, and then these wildfires are going to occur, and we go all the way from vegetation to bare soil or some kind of like shrubs at some time. And if we look at how the soil is going to change, after the wildfire, we have a thin layer of ash, and then we have the burnt soil and the remaining soil. So we incorporate all these changes in our mathematical model to see how these changes are going to impact something like groundwater storage in the Cosumnes. First, we look at something like evapotranspiration, trying to understand how wildfire impacts evaporation and transpiration. We can see in this picture on the left how evapotranspiration changes in the post-fire condition. In red, we do have like where we have decrease in evapotranspiration, and in blue, where we have increase in evapotranspiration. And these changes in evapotranspiration mostly occur in the area, in the burn area, as you can see on the figure on the right. I put where the burn area is. We do observe as mostly decrease in evapotranspiration, which makes sense because after a wildfire, we do not have vegetation, so we do not have any evapotranspiration demand. So which means that all the water is going to stay in the soil instead of going back to the atmosphere by evapotranspiration. However, some areas show an increase of wildfire, of evapotranspiration. This can be counterintuitive. As I say, we remove the vegetation, so we could expect to have a decrease in evapotranspiration. But because the soil moisture is going to increase, as Katia mentioned before, we are going to have more water available for evaporation. If we look at something like snow, keeping in mind also that in our model, we are simulating all the water cycle, so we can really understand how this kind of component of the water cycle are going to change. In this picture, I'm showing how the snow is changed throughout the year. In blue, we have how the normal snow in a year without fire. And in red, we do have after the wildfire. Basically, after the wildfire, the snow does increase because we do not have canopy again. When you have vegetation, the vegetation is going to retain the snow, and this snow is going back to the atmosphere. In the post-fire condition, because we do not have any vegetation, the snow is going to accumulate in the soil and increase. As the snow is going to accumulate in the soil in winter, it means that in the summer and also late spring, we are going to have an increase in snow melt. An increase in snow melt means an increase in runoff. As you can see in this picture, I'm showing how surface water storage changes throughout the year. In blue, we have how the surface water storage look in a normal year, and in red, in the post-fire condition. And there is an increase in snow and in stream flow in the post-fire condition because we do observe an increase in snow. In this picture on the left, I'm showing where we observe this increase in stream flow. Again, because we are solving this kind of the water cycle at a meter scale, we can really understand where in the watershed we do observe these changes. Basically, this increase is mostly down in the Central Valley, as you can see this in this picture. And because this wildfire, by increasing snow, by decreasing evapotranspiration, by increasing stream flow, they are also increasing groundwater, as we can see it on the right in this picture, indicated by the blue. All the blue area indicate where in the watershed we observe an increase in groundwater in the post-fire condition. To summarize, we use a high resolution, high fidelity, and physics-based model to be able to reproduce how wildfire changes our landscape and how these changes reshape the water cycle in California. Before to make any conclusion, we make sure that our model is able to reproduce both satellite-based products and ground measurements. We observed that groundwater and surface water storage increase in the post-fire condition, as also Katya mentioned it before in the stream flow. This increase is mostly observed in summer. And it's because there is a decrease in evapotranspiration because wildfire damaged vegetation, and then an increase in snow. So thank you.
Thank you so much, Faji. Okay, we have some questions coming in. So my first question coming from the audience is, I know you talked about an increase in snowpack, and also Katya talked about snowpack as well. Is there expected, even if we don't have, even if the fire damage is like holding fire damage steady, will snowfall increase with changing climate? Well, what are the extremes? How are the extremes going to look like? I know both of you talked about how California is an extreme weather place, right? Location. Is there an idea of how climate change is going to change the snowfall?
For sure, like because in California, the climate is going to increase, like the temperature is going to increase especially by the end of the century, and it depends, it can be like 2 to 4 degrees Celsius increase in temperature. So it means that whatever we are observing today in terms of like snow falling in the Sierra Nevada and then the snow melting, we are going to shift from snow to rain. So this rain is going to still fall in the Sierra Nevada, but then there is not going to be a delay because it's just rain, it's going to flow down.
Right. Great. Thank you. My second question is, did the model have any component of vegetation recovery? So was it reflected an impact on moisture or water storage? Just was it incorporated into the model in some way?
So in the model, we did not incorporate any vegetation recovery. We assume that the vegetation is going to be static first, because also vegetation recovery takes time to come back. After typically 1 water year after a fire, there is little changes in vegetation that can make like a lot of changes. But yeah, for sure, if you do, that's why we limit ourselves for just 1 year. If we want to do like something like 5 years, we do have to include vegetation recovery in the model.
All right, thank you. So let's bring both Katya and Jen back. And I know we have several more questions. We had a lot of questions rolling in. So why don't I ask Jen, do you have a question ready?
I do. So maybe this is a question that both Katya and Fadia can answer. We got a few questions about wildfires in more populated areas. The first is it possible to allow natural wildfires in more populated areas? And the second question sort of relates to whether you're aware of any discussions happening in the state about disallowing dwellings in fire-prone areas.
I mean, I think in terms, like, especially second question or second part of this question, there is I mean, I think the pressure is from insurance companies mostly in terms of disallowing dwellings, not so much from policy, and the high insurance cost of owning a house in a place where if it burns down, there is no insurance discourages people from building there. So there's kind of like a economic push from, yeah, not so much policy, but just the fact that it costs a lot. I think I don't think it's a good idea to have wildfires in urban areas for just like the ones that I've talked about, for example, for many reasons. So controlled burning makes a lot more sense because it's more controlled, as it says. But yeah, the wildfire management is more specifically for areas that do have, like, it's like forest land or a national park system, just because you do need a pretty large area and some uncertainty around where the wildfire is going to go about having someone like extinguishing lines around houses. Yeah.
Yeah, I would add also, like, because in our study, they haven't shown it here, but we observe that depending on the area, actually, these wildfires are not going to make any changes. To be able to see any changes in terms of stream flow, given the hydrology of California, this wildfire has to be in some particular area to be able to see even changes in hydrology downstream. So we really need to, that's why also we use this kind of model that to capture all the hydrology and to be able to see this sensitivity depending on the area.
Thanks both. Oh, Dee, I think you're on mute.
It always happens once. All right. So my question for both of you, do your research bring in past historical fire data, like human impact, to understand how the ecology and vegetation and forest land, how they recovered? Or is it something you're just using kind of present day scenario?
Yeah, I can speak for that one myself. So there's a lot of research on the Lead Creek Basin, especially from Scott Stevens' lab group, and they did use dendrochronology on trees in a lead, so essentially you just like figure out the tree scars within the tree, and like that's how you figure out how often fires occurred. And some research shows, well, like from that analysis, the fire return period interval in the Lead Creek Basin used to be 6.3 years. So every 6.3 years, there would be a fire in the basin, not like a specific location where it's again. However, now, like after wildfire suppression ended and now the fires are back to a 6.9 fire return interval. So again, the point is, it's actually quite similar to what we used to have. And I think there's a lot of scare of wildfires that they would never return back to quote unquote natural system. And again, natural, it's more like what we used to see. There's still some fire management from native populations, for example. But yeah, anyway, so Illit is definitely a place that shows that we could return back to having wildfires looking at historical data.
So I have a couple clarifying questions that we've got from audience members. The first is, do controlled burns produce similar hydrological effects as natural wildfires?
I can answer, like, it depends also on the scale on which, it's everything related to the scale and where. So I think that we should care about, like, where we have this controlled burn area and also the scale, because it's just like small scale, again, as I mentioned before, some of these controlled wildfires occur in the small scale, so it's really hard to see any kind of like changes, but it depends on the scale and it depends on what. But if these controlled bonfire like at that, like as natural, they're going to produce similar kind of changes.
Yeah, and also controlled burns generally tend to focus on very low severity, so you like really don't change vegetation as much as you just remove like the litter and stuff. So you kind of do need some high severity areas and small patches to produce change. Yeah, so less change from controlled burns.
Thanks both. And then there was just one clarifying question that an audience member had. Will there be more drought or less drought with climate change in California?
I mean, it depends on the type of scenario that you are using on type of model, but there is a consensus that this is going to be, it depends also like on, from compared to what kind of like baseline are you going to see? There is going to be more drought or there's going to be like more extremes, because based on another study that we have done with other colleagues at Berkeley, we observed that basically we are going to have like more extreme precipitation in California, which is also like happening right now, right? We know that kind of you can have like some pretty rainy day, and these rainy days are going to be like even intense in the future. So for sure we have to plan for like more extreme rain, but then these rain are going to happen like in just few very short period, and then it's going to be dry. So it depends. Some kind of studies are saying that this dry that we observe in the past, and we are not going to observe them in the future. For sure. But in the future, compared to what's going to look the future, we are sure going to have dry and wet year.
Great. There's been a few questions around the idea of sharing findings with policymakers for the purpose of restricting maybe building in high prone fire danger areas, building water storages to prepare for snow to turn into rain, right, in response to the climate change. So questions around sort of how we mitigate what we're seeing and how policymakers can regulate maybe building in these areas, or again, how we respond through water storage.
Do you want to go?
Yeah, it's a pretty hard question, as in I try to convey like my findings, and I do actually, I participate in a lot of Yosemite hydroclimate meetings, and there's a lot of like dam operators who attend and forest managers. So in that realm, people do understand it, but I don't know if research findings have directly found policy making and money to like build bigger storage. But I do think it's necessary. Even about wildfires, you're gonna just have less uncertain, or you're gonna be less certain of the snowpack, for example, because you don't have like a memory of how much water you have. So you're gonna have like flooding and etc. So I'm hopeful, but yeah, not really sure if anything has been changed.
Yeah, I think that we need a lot of more science to be able to understand this wildfire, and because also if these science are going to tell us like what the recovery of the system, how this system is going to react and everything, I think yeah, we need more.
So hopefully we'll develop this further soon.
Thanks both. So we got a couple of questions for both of you. It seems like you've used the Illinois Creek Basin as a model, and Fadji, you've modeled the Cosumnes. We're curious to know if your findings are unique to the Sierra Nevadas in California, or could your research be relevant to other Western states who are impacted by severe droughts and wildfires?
So I can go first to answer the finding. Like when we did this study, we make sure to compare our finding with many other studies that have been performed. Basically, in the United States, California, but there is like there are studies in Spain or Australia with different kind of wildfire, and basically we are observing kind of similar patterning. If after wildfire, we are going to have like less evapotranspiration, so moisture is going to increase. But what can be particular to the state of California is kind of because we have this Sierra Nevada and this snow, and there's this gradient that this flow is going to fall to flow downstream, that in case of like when we are going to observe, because in California, basically this wildfire occurring in the Sierra, and then we observe this change in the Central Valley. So it's particular to like the geography of California and topography of California. If some other states or some other countries have the similar kind of like geography and topography, we are going to observe. But in terms of like how the hydrology changes at small scale, something like evapotranspiration, something like snow, something like soil moisture, it's not like tied to the particular watershed that we study.
Yeah, I think a Lead Creek Basin could be extended to a lot of areas in the Sierra Nevada, but I would be, yeah, topography and like presence of snowpack and type of vegetation would matter. So I would not just be like, oh yeah, this could be applied anywhere. But there are a lot of areas in Sierra Nevada that look a lot like the Lead Creek Basin.
That's why also like we need to understand like the water cycle, because the water cycle is different components. So it's like what's particular to the watershed that we study is because we are adding all these kind of component. And if you add all these kind of component, for sure your response is going to be unique. But you can understand from how this one like individual component change.
Great. Thank you both for answering that question. So in terms of wildfires, a question came in about whether or not it seems to be that it's more about the extent to which the wildfire is spreading as opposed to the number of wildfires. Can you guys comment on, have policies been in place, the policies that have been in place, have they actually decreased the number, not the extent necessarily, but the number of wildfires? Like I know, Katya, you mentioned Smokey the Bear, right? So how have the numbers changed through time?
I mean, I have a graph somewhere, which I wish I shared, but it's mostly for Yosemite area. And because it is dendrochronology based, so you can like really go back in time, but it does look like some constant level of wildfires. And then there's a peak from when everything, like there's no management because the native populations were like colonized essentially by Spanish colonial invasions, and then it's just a complete drop. So like from the like a really long record, there's some constant wildfire use, and then it just dropped. Yeah.
All right, so we've got a question from another listener. Some forest harvesting literature says that the reduced evapotranspiration talked about today leads to more water. But with fires we've seen, some of that water is leaving the catchment in floods and ash-laden debris flows. So how do we balance talking about water availability and water usability for human use?
Sorry.
Go ahead.
Yeah, so that actually comes up in my presentations quite a lot. And again, I'm going to focus on the Lead Creek Basin a lot, just that's something I do know. But we are not, like we have done modeling and we do have a stream gauge down the stream, and we're not actually observing like flooding events. And we're not seeing water quality decrease. And we actually do have an explanation for that. And that's going back to mixed severity, pretty small fires. You're not removing giant areas of vegetation and making your soil impermeable to water because small, like not that severe wildfires, they do remove some trees, but they don't leave large patches that promote overland flow. Or again, another thing that comes up is the soil properties change after wildfires, where the soils become less permeable, and so therefore you get overland flow and flooding. We're not observing that because we are not just wiping out large areas. And that goes back to the whole, like, let's not have large, high severity fires, which are not really like natural. I mean, some are, but generally mixed severity fires is what we used to observe.
Great, thank you. So our next question is, who actually determines if a wildfire is going to be labeled as catastrophic, and have these guidelines for labeling a catastrophic wildfire been accurate, right? If we let a wildfire burn, has it ever gotten out of hand where maybe those guidelines were wrong?
Sorry, Faji, if you have something to say. To go first. I don't actually know if there's specific definitions other than when you see one, like again, campfire, definitely catastrophic because no matter how much resources we were trying to put on it to extinguish it, we could not. Others, I mean, could be borderline, right? Like if you plan for a wildfire to not reach certain structures, but yet it does and it destroys it. I mean, it's borderline, but one thing that people do look at is like the mix of severity. It could be a large fire, but if it's just like low severity, which essentially means you might remove some litter, you might like scorch the trees, but generally like you're not killing things. That's like one way to label, but yeah, I'm not sure if there's a definitive line, like this fire is catastrophic versus this one's not.
Thanks for that answer, Katya. I have a question for Faji. How has high-performance computing enabled you to assess other impacts of climate change and wildfires on watershed hydrology?
So we have been using this Cosumnes watershed to perform like many other kind of study. First, as I explained in this talk, because we really want to add every component of in the water cycle to be able to observe the aggregated response, which is really important in California. So we are going to simulate like many kind of processes, which means many kind of equation, which means like many time of high performance computing. So we have been using high performance computing in the Cosumnes watershed to understand what the impact of transition between severe period of drought and wait. And as you can see, like from 2013 to 2017, we observed both severe drought and wait. And this kind of transition, as I mentioned before, are going to be the future of California. So we really need to understand how this is going to impact. And one question also in California, people are thinking like, if after a dry, when we are going to have a wet year, this wet year is going to negate the impact of the drought. So we can try to understand how this is going to change the hydrology of California. We use also high performance computing to project the hydrology by the end of the century, using business as usual. What if we keep our emission as we are doing it right now? How this is going to change the hydrology of California? How our groundwater changes are going to look by the end of the century? So we're really using high performance computing because this high performance computing allows us to really understand the complete picture of water cycle, to understand some of the most environmental challenges of hydrologic challenge in the state of California.
Great, thank you. So do you all look at the cost of treating the water in terms of the increased wildfire, how that affects water quality? If the runoff increases, then enters the streams, and then there's a cost associated with that. And what does that look like?
I don't have numbers, but yeah, there's big fires that happen in Colorado somewhere where like the basin or like a reservoir had to spend, I think, in the order of like billions of dollars to dredge it. That's certainly a thing. But again, usually the association is with like quite large fires that wipe everything out, and there's no vegetation and the soil is quite different. So I don't have numbers myself, just because that's not something we've observed in the wet ever.
Yeah, we haven't looked also at like how these wildfires are going to change water quality. We just look at the quantity for sure, because the stream flow is going to increase. And also if you think about like the future, when you are going to have more rainfall, so it means that after a wildfire is going to be like more catastrophic changes in stream flow. It's going to be a big problem for water quality.
It's definitely an important thing to consider. Like, I do not want to take away from the fact like, yay, stream flow, it's great. There's certain costs that are associated with, well, like, are you seeing more erosion? I'm saying we're not in our watershed, but it's certainly a thing that could happen elsewhere.
And also one question to ask to think about is like how our infrastructure today, because they are like, these have been designed on historical record, and this historical record will no longer be like valid in the future. So we really need to think about our dam, the capacity of our reservoir, and all this kind of thing.
Well, thanks both for those answers to all of these questions. We got some really great questions from the audience, so we appreciate you asking those. Before we wrap up, I just want to check in with both Faji and Katya. Are there any sort of last things that you would like to leave the audience with about your research? And I've got a question for you. You guys have both been doing some fascinating research and have come to some really interesting conclusions. Where is your research going to take you next? What are you looking at, in the future? How do you think you'll be able to apply this and inform future research?
I mean, I would say that the future is complex, and the present is already complex. The future is going to be even more complex. So there are like more challenges that we need to tackle in the future. So I'm very excited about the future. I mean, studying the future also to be able to provide people, because we need water. Water is 70% of our body. We need water to drink. It's like just drink water right now. We need water every time, and we really need to think about our water. And because the future is going to be complex, we need to tackle these kind of challenges. So there are a lot of challenges in the future, like wildfire, like climate change, like by itself, understanding climate change and how this is going to change hydrology, how this is going to change, like based on different kind of like area, and also what's the interaction between humans and water, and also having policy. So there are a lot of features to do in the future about water.
Yeah, that's kind of my similar conclusion about the biggest thing I took away. It's everything is connected and there's so many interactions and there's almost like no way to really stop. Yeah, it's like it's infinite in terms of how many different connections and how one thing affects another. And so I have not really done a lot of work in terms of human effect on those systems, but like that's a huge different topic as well.
Yeah. And also something to think about the future, because as I mentioned, the future is going to be complex. We need to think also about like our ability to solve like problem that's going to increase by high performance computing. We know that like the computer are going to be fast and fast. So we will be able to like, even if the future is going to be complex, we will have the material and also the ability to solve this kind of problems. So it's also thinking about how are we going to merge our advances in high performance computing and the challenges that we are going to face in the future.
Well, that's really exciting, and I'm looking forward to learning more about your research as you move forward. Before we close, I just want to say thank you again, Katya and Faji, for your presentations. They were very informative, and I'd also like to thank the audience for their really interesting questions and appreciate their tuning in. As we said at the front of the program, if you'd like to stay up to date on research coming out of either Berkeley Lab or UC Berkeley, you can visit both of our websites. Science at Cal is scienceatcal.berkeley.edu, and Berkeley Lab is www.lbl.gov. So thanks again, everybody. Have a great afternoon, and we look forward to seeing you at the next Midday Science Cafe. Bye-bye.
Bye.